Hi everyone, welcome into lecture number 13 of linear algebra. This lecture is on the least squares method of solving or approximating a solution to a system of equations. So let's start by setting up the situation here. Let's consider a matrix A that's in R m by n, so it's an m by n matrix, and a vector B in Rm. And further, let's suppose that this vector B is not in the range or the image of A. So the book calls this the range. We've called it the image, but let's suppose that it's not in the image of A. Then here's what the situation looks like, right? So remember that a matrix A can be thought of as a linear transformation by multiplication, right? A linear transformation from Rn, and then the matrix does its multiplication, and every vector in Rn is then mapped to a vector in Rm. All right, and I'm just drawing these look two-dimensional just so we can draw them. But for the sake of this argument, let's say that the image of this matrix, or the range of this matrix, it's always a subspace, right? Always. So let's say that it is represented by this line in our two-dimensional schematic here. Really, it's m-dimensional space, so this is just, let's say, a k-dimensional subspace for which k is less than m. So it doesn't fill out the entire space Rm. And then our assumption up here is that B is not in the image of A. So that means that B is maybe, say, this vector. Could be any vector, but I'm just picking this one. So there's the vector B. And in this scenario, what we would like to do is try to solve, or let's suppose that we are given, given the system of equations, A times x equals B. So then the system, in this case, AX equals B, this is going to be inconsistent, right? Because the idea is that any x that comes from this domain space over here, let's just say this one, any x is going to be mapped to a point in Rm. So any x in Rn is going to be mapped by A to a point in Rm, or a vector in Rm, that lives in the image space, right? It has to be in the image space. So our system is then inconsistent, has no solution, right? If we try to solve this system of equations, Ax equals B, we will not find a solution. B is not in the column space of A, which is the image space of A, right? So our goal then is to try to find a best fit solution in some sense over here, right? So try to find an x that gets us as close as possible to B. So this is the goal here. So find an x in the space Rn such that, that gives A times x as close as possible. So I'll put this in quotation marks, but as close as possible to B. And there's different ways to measure closeness, but we're going to measure closeness in the most obvious sense, all right? And so here's the idea. Let's suppose I pick this vector x right here, this one that I've already drawn, and its image obviously has to live in the range, right? So maybe its image is this vector, right? So maybe this is Ax over here. So x from the domain maps to Ax over here in the image space. Then what we can do is we can take the difference vector. So we can take the difference, I'll draw this one in orange. We can take this difference vector right here, which I'm going to label r of x. All right, so this vector r of x, it has a name, but this vector r of x is going to be just defined to be the difference of b, which is our vector of the right hand side, so that's our given vector that's not in the image space, minus the image of x from the domain space, right? So it's this difference vector, and this is going to be called the residual vector of the system. So this is and it's associated to x, right? So this residual vector is dependent on the choice of x in the domain over here. So really this r you could think of as a function itself. But this is called the residual of x. So the residual vector of x. And so what we're going to do is we are going to, so again I said we need to choose or make a determination here of how we're going to measure close, this word close, right, as close as possible between the vector Ax and the vector B. And the way that we're going to do it is we're going to minimize the length of this residual, all right? So we're going to call this the least squares solution, but the least, so I'll just define it now, I guess. But the least squares solution x of the system ax equals b is the vector x in Rm, n in the domain space, that minimizes the residual. Now, what do I mean by minimizes? Well, I mean minimizes the length, right? So I'll even write that. Minimizes the length of the residual vector. And that was what we called R of x, right? So it's defined by this difference, though. All right, so then we're looking for, in that case, we want this, right? The norm or the length of R of x to be minimum. So, and it turns out this happens, and we know this just from our previous studies, right? But this is minimized when what's going to happen. So just look back at this picture. Everything here is like the geometry of two-dimensional space, which we're familiar with. So this is going to be minimized. I'll redraw it over here with what we're going to call our solution vector here, right? But it's going to be minimized when the following is true. So there's, remember, our image space of A, and we have our vector B that is not in the image. So it's not in the column space of A. And so our vector R is going to be minimized. It's going to be the shortest length, right, when it forms a perfect right angle, pi over 2 angle here. So in other words, when R of x is orthogonal to this projection vector down here. All right, so this vector we'll call P equals A times x. And so again, the idea here is that we want to minimize, so we want that to be a right angle. We want to minimize the length of the residual. All right, and so just by geometry, we know that that's going to be true. So this is going to be true when R of x is orthogonal to this vector that I've called the projection vector P, which is A times x. All right, and so what that means then is that this is orthogonal to so the solution that we're looking for, right, is going to be orthogonal to the image space. All right, so thus the least squares, I'm just going to call this LS, but the LS solution x occurs when R of x is in the orthogonal complement of the image space. But remember, our fundamental subspace theorem says that the image space of R of A, sorry, the orthogonal complement of R of A, right, is the null space of A transpose. So we're looking then for a vector for which, a vector x for which R of x, the residual, is in the null space here. All right, so that's going to be our defining factor. That, remember, the A transpose goes back this way, right? A transpose maps in this direction, maps from Rm back to Rn. And so this vector right here, this R of x that we're looking for, we want it to be in the null space, just map back to 0 over here in the what was our domain space, right? Okay, so we're basically there now, right? So what do we want? Well, for this vector to be in the null space, what do we mean? Or what do we need, I should say? Well, then, for this to be, let me just write it all out here. But so R of x is in the null space of A transpose if and only if A transpose times R of x is equal to the 0 vector. All right, but we have a formula for R of x up here, right? Our residual is this difference vector. So we can write this then as A transpose times B minus A times x should be equal to the 0 vector. And a little rearranging then, right? So another or here, says that what? Well, this is a minus, we can move this over, but first we have to distribute. So the equation is going to become A transpose times A times x equals A transpose times B. All right, and so this right here is now the equation that we're going to solve to find our least squares solution x. This is called the normal equation, or the normal equations of our system. So this is the normal equation. It's called normal equations, plural sometimes, because really this is a system of equations, right? But the normal equation for our system, ax equals b. All right, and there's a theorem in our text, which I won't prove here, but you should read through it. It says that the solution of this equation is unique. So the solution of the normal equations is unique. solution x. Again, this x still lives in Rn, right, of the normal equations is unique. That means there's only one, right? So therefore our least squares solution is going to be unique as well. All right, and so by solving this system, we will get our answer, right, to the best fit solution up here as we've defined closeness. So it'll minimize our residual vector, the length of our residual vector. Okay, so a couple other things here, just definitions, and then from then on, after we finish off these definitions, then we'll just do examples. We've defined the residual, we've defined the projection in one sense, it's a times x, but there's another way to write down the projection vector. So let me just rewrite all these definitions so that we have them. But r of x, again, this is defined to be b minus a times x. This is the residual of x with respect to this system, right? So everything's with respect to this system. Our projection vector p onto the image space, right? This is the projection of b onto the image space. And this is given by the following formula, which again, it's going to be an exercise for you, a homework exercise for you guys to work out this formula. But this one is a times a transpose a inverse, that whole thing inverse, times a transpose times b. You just get this by kind of working out some, you can almost see how you're going to get this from this equation right here, right? But this vector right here, this is the projection. So this is the projection of B onto the image space of A, so onto R of A. All right, and then the matrix itself here is important. So this capital P with no hat on it, this is just going to be the matrix here. So A transpose A, inverse A transpose. This is the projection matrix. And we'll see that this is an important matrix. So this matrix you can use to multiply by any vector in Rm and project it onto the image space of the matrix A. All right, so that's what the matrix P does. The matrix P will take any vector over here in Rm and find its projection onto the image space of A. All right, and so that's useful for many, many reasons. But those are just definitions, and now we've set up the whole scenario here, set up the method. This is the main equation that we want to look at, right? A transpose A times x equals A transpose B. That's what we're going to solve. We're going to solve this for x, right? That's our goal. So let's try some examples now and see how this works. So we'll start with an example with just a system of equations there's a system of equations in R2, but it's going to be 3 equations with 2 unknowns. So here's our first example. So we want to find the least squares solution to this system. And this system's, like I said, it's going to have 3 equations, 2 unknowns. So it's going to be overdetermined, right? That's why it has no solution. It might have a solution. By the way, if there is a solution, then the least squares solution will coincide with it, right? The projection of a vector onto itself is itself. So the least squares will give you the correct solution if your system is consistent. It's kind of overkill to do it this way, but it will work. So the third equation then here is x1 minus 2x2 equals 20. The second equation was 2x1 plus x2 equals 5. All right, so here's your 3 equations, 2 unknowns. What I'd like you guys to do is take a moment, write the system out in matrix form, and then try to, just by finding A transpose, right, turn this into its normal equations, and then once you have the normal equations, try to solve the normal equations to get x. All right, so take a moment to work on this one, and when you come back, we'll do it together. All right, let's see how you did. The first step is to write this in a matrix equation, right? So the first step, I'm just going to write this out. The coefficient matrix, the first column is -1, 2, 1. The second column is 1, 1, -2. The vector of the unknowns, those are x1 and x2. And the right-hand side, the vector b is 10, 5, and then 20. Okay, and so this is then the matrix A. This is the vector B. X is, of course, just the unknowns that we want to solve for. So we're going to find the best fit solution here. We need to start by then working out A transpose A, A transpose B. So let's just write out all the pieces here. A transpose is, of course, the matrix whose first row is -1, 2, 1 with the column of A. And second row is the second column of A. So 1, 1, -2. And then from here, we can work out those two things, right? So A transpose A and A transpose B. We can work each of those out. So A transpose A is going to end up being a 2 by 2 matrix, right? So when we work this out, we'll see what we get. So this one, the 1, 1 position, right, is going to just be the sums of the squares. So 1 plus 4 plus 1, so that's 6. Same with the 2, 2 position. So 1 plus 1 plus 4, that's also 6, right? And then the other two are going to be equal as well, right? The 1, 2 and the 2, 1, this is going to be symmetric because of the way this is built, right? So the 1, 2 is going to be -1, -2, so that's -3 plus 2. So it's going to be -1. And same thing down here, right? So there's our matrix. So 6, -1, -1, 6. There's our matrix A transpose A. Similarly, we have our A transpose B. This is going to be the new right-hand side of our system, right? So A transpose B is going to be -1, 2, 1, 1, 1, -2, multiplied by the vector B, which is 10, 5, 20. This is going to be a vector in R2 now, right? Yep. So this is going to be in R2. And so this one's going to be -10 plus 10 plus 20. So that's going to be 20. And then the next one's going to be 10 plus 5, which is 15, minus 40. So that's going to be -25. All right. And so there's the new right-hand side. So now we're ready to write down the normal equations for this system. So let's do that now. The normal equations become, remember the normal equations are A transpose A times X equals A transpose B. So that's what we've got here. Our A transpose A matrix is this one. So we'll have 6, -1, -1, 6 times the vector X. So that's X1, X2. Those are our unknowns. And then on the right side, A transpose B is this vector 20, -25. And so our goal now is to solve the normal equations. And we can do this by using any different method that we know for systems of 2 equations and 2 unknowns. This is already in matrix form, and so I think for this one what I'd like to do is solve this one using Kramer's rule. Just to kind of make this a little bit nicer to write down, let's rename this matrix here C. We'll call this matrix X, and then on the right hand side this was B. Let's just call this one D. So we want to solve this equation for for X using Kramer's rule. So as we know, Kramer's rule involves taking the determinant of this matrix and then a couple of other matrices, right? So first of all, we need to know the determinant of C. That's going to be part of our answer, right? The determinant of C is just going to be 36 minus 1. So that's going to be 35, right? So 36 minus 1 is 35. And then we need to build, in Kramer's rule, the other matrices. So the matrix C1 is going to be the matrix that we obtain by replacing the first column of C by the column vector D, which is the right-hand side. It's A transpose B. I just called that D. So this one will be 20, -25 over here, and then -1, 6 here. And we just carefully work out the determinant of this. So I've written equals, but really we want to have like an arrow here. So the determinant of C1 is going to be 120 minus 25. Okay, and so that's going to be 95, right? Next, we need to make the matrix C2. So the matrix C2 we get by replacing the second column of C by the column vector D. So this will be 6, -1 in the first column, and then it's going to be 20, -25 in the second column. And then we can take the determinant of C2. This one's going to be -150, right? So -150 minus a negative. So that's going to be plus 20. And so this one's going to be -130. And so at this point, we can write down our solution, right? Because we know from Kramer's rule that X1 is equal to the determinant of C1 divided by the determinant of C. So in this case, that's going to be 95, which we computed, divided by 35. All right, and so there's some reduction that can be done. I'm going to leave it in this form. You can reduce it if you want. But the second term is, or the second entry, x2, is always going to be C2, determinant of C2, divided by determinant of C. And so in this case, for this one, this is going to be negative 130 over 35. And then just remember, up here we were trying to solve this system, right? So the answers for x1 and x2, the least square solution, so the best fit solution is going to be these two. So we'll say our vector x here, our vector x is going to be the vector, our best fit solution here is going to be the vector 95 over 35 in the first component and negative 130 over 35 in the second component. All right, so there's an example of how the least squares solution can be found. right, let's see how you guys did. So again, we're going to go through the same process we did before. Notice that we can kind of streamline some of this if we want to find the inverse of this matrix as opposed to doing Kramer's rule. So what we can do is the following. Remember, our vector x is equal to A transpose A inverse times A transpose times B. So if we just work out all the parts of this, this is our matrix A, this is our vector, but matrix B. We can find the B and M by just carefully working out this equation, right? So let's do it in parts. Let's start with our A transpose. You have to do almost all of the same stuff that we did in the previous example. But A transpose is going to have ones along the first row now. -1, 0, 1, 2 in the second row. And then we need to multiply this by A, find the inverse, and then also multiply this by B, right? So let's do A transpose B first. That's going to give us a 2 by 1 vector, right? So a vector in R2. 1, 1, 1, 1 again along the first row. -1, 0, 1, 2 in the second row. 0, 1, 3, 9. Those are our entries. So the first entry is just add all these up. That'll be 13. The second entry, we have 0 plus 0. Those are gone. And then 3 plus 18. So that's going to be 21. All right. And so there's our vector A transpose B. So that's something. Now we need our A transpose A, and then we'll have to find its inverse. But it's a 2 by 2 matrix in this case. So it's going to be pretty straightforward. So we just need to multiply this all out. And we know how this works, right? It's going to be a symmetric matrix. We've seen this once already. So this first one, this is 4. This next one is 1 plus 0 plus 1 plus 4. So that's 6 down here. And then the rest of these we're going to add, just they're going to be the same. It's symmetric again, right? So -1, 0, 1, that's 0, 2. So this is 2 and 2. Okay, and then we need the inverse. So of course, to find the inverse, we also need to know the determinant. So A transpose A determinant is going to be 24 minus 4. So that's just going to be 20. And so that means that our inverse matrix, A transpose A inverse, is going to be 1 over 20 times these two switch spots and these two switch signs. Right? And so there's that. And now we can just multiply just by, multiply this matrix, right, times this vector. So I've highlighted in a very odd way here, but this matrix times this vector. So that's what we have to do. We'll have our solution then. So our x hat is going to be 1 over 20 times inverse matrix, 6, -2, -2, 4, times vector A transpose B, 13, 21. And now we just carefully work this out and see what we get. So this is going to be 6 times 13, that's 78, right? Minus 2 times 21, so minus 42 in the first component. We have the 1 over 20 out front. And then the second component is going to be minus 26, -26, plus 84. And that's the second component here. And so then we very carefully work this out. So the 1 over 20 stays, and then we just subtract, right? So 78 minus 42, that's going to be 36. And then 84 minus 26, that's going to be 58, right? 58. And then we can reduce this a little bit. So we have 36 over 20. These are each divisible by 2 is all. So this is going to be 18. I guess 4 goes into each of those, right? So that's going to end up being 9/5 in the first component. And then the second component is going to be, This is going to be 29/10. That's the best we can do there. So 29/10 in the second component. And then remember what these answers to our x bar, what these correspond to. So these are the values of B and M from our linear system, right? So for our equation of our line. So we just found B and M. So what we found then is that B is equal to 9/5 and M is equal to 29/10. And so the equation of our best fit line is then y equals mx plus b, or in this we have these numbers, right? So y equals 29 over 10 times x plus 9 over 5. And so that's the equation of the line that best fits the data given by the table for this example. All right? So this one we'll just do together, but this is an example number 4. Sometimes when you're given data, a line is not the best shape for you to try to fit the data to. And sometimes just by plotting the data, you can see that you should have a different shape, or maybe you have another reason based on when you gathered the data for suspecting that a different shape, a different kind of curve, should be the best fit curve, right? So what we would like to do then is adapt the data for the following to a best fit circle. So adapt to a best fit circle. For the following data, this is slightly different data, okay? So this data now, it's not slightly different, it's very different. But here's the point. So we're going to have 4 points again. So -1, -2, there's 1 point, 0, 2.4, second point, 1.1, and -1 point, -1 and then just -4. That's the next data point. And then 2.4 and -1.6. So we want to try to find the best fit circle to fit this data. And again, in this case, we're being told that we should find the best fit circle. But you might have a good reason for doing this, right? If you're not told, maybe you know that the measurements you're taking should fit on a circle. Maybe, with only 4 points, it's hard to say that that should fit on a circle just by looking at the plot, but you can maybe tell that they shouldn't be on a line, right? But anyway, we'll just go with this just because we were told to, right, to find the best fit circle. So we know then that to find a circle, we need to find the center of the circle and the radius of the circle, and that the equation that we're looking for will then be of the form x minus h squared plus y minus k squared equals rho squared, I'll call it, for radius. R means residual now, so I want to call it something different. But given all this data, this, by the way, is not a linear equation, right? So given this data and this equation, we need to solve for h, k, and rho, right? So our to be determined here are h, k, and then this rho, the radius, or at least rho squared, right? To get the equation here. So let's write it that way, rho squared, because our solution is going to be this equation, right? So we just need to find rho squared. But to do that, though, we have this nonlinear equation. We need to find a linear equation that's going to work for us, right? So let's take this equation and multiply it out, the left-hand side, right? So the left-hand side is going to say x squared minus 2x times h plus h squared plus y squared minus 2y times k plus k squared equals rho squared. And then what we can do is we can rearrange all of this to get what are going to be the numbers. Remember, we're going to plug in these numbers from our data, right, to get the system of equations. And so the things that are going to just be numbers and not have any of our unknowns are going to be x squared and y squared. So we'll leave these alone on the left-hand side. It'll end up being on the right, but on the left-hand side. And then we'll move everything else over to the other side. So now on this side, we're going to have 2x times h plus 2y times k. Those get added over. And then we're going to have plus rho squared minus h squared minus k squared. Right? And I'm going to group all that together. All right. Now, what do we do? Well, now we have an equation where we're going to have number, right? After we plug in the data, we're going to have numbers, a number coefficient times h, a number coefficient times y, times k, plus a number, right? And this number here, we can just call by a single name. So we're going to use this number to find our rho squared at the very end, but we'll call this, let's say, we'll call this thing, just give it a name, right? Let's call this one J. Why not, right? HKJ. Why not? So we'll call it that. And so then our system is going to be determined by the following. So we're going to have our matrix equation is going to come from, I'm going to rewrite this now, 2x times h plus 2y times k. My parentheses should be this way. So coefficient h, coefficient k, plus j, right? This term j equals, so that's just 1j, by the way, right? Which is 1j equals on this side x squared plus y squared. Okay? So now to build our system, we just need to plug in this data in for these coefficients, and then that'll give us our equations, right? So let me write the system over here. So this one's going to be negative 2h plus, this one's going to be negative 4k plus 1j equals x squared plus y squared. So this is going to be 1 squared plus 4 squared, so this one equals 5. Okay, and then we can go through the rest of this. So 0h, right, plus, next one's going to be 4.8k plus j equals 2.4 squared, right, over here, 0 plus 2.4 squared. So that's that. And then over here we have 2.2, the next one, 2.2h plus, this one's going to be minus 8k plus j equals, on this side it's going to be 16 plus 1.21, so that's 17.21, right? And then finally we have 4.8h plus, this one's going to be negative 3.2k plus 1j equals the sum of the squares of these ones, right? So 2.4 squared plus negative 1.6 squared. All right, so why don't you guys take a minute. I'm going to just pause the video here, or put up the pause screen here, just for you to finish working this part out. So this is the system that we need to solve. Once we have h, k, and j, we'll come back together and we'll finish this together. Alright guys, so I hope you had a chance to work this out. I'm just going to kind of recap everything that I did to solve this one, to finish this one off. You don't need to see all the details, but the matrix equation comes straight from this, right? So the matrix equation, I'll write this out. The matrix equation is the following. So just from our work here, it's minus 2, 0, 2.2, 4.8 in the first column, and then negative 4, 4.8, negative 8, negative 3.2 in the second column, and then all ones in the third column. The unknown vectors in order here are h, k, and then j, not the vectors, but the unknown constants that we're trying to solve for here. And then the right-hand side turns out being, just if you work this all out, it's 5, 5.76, 17.21, and then 8.32. And so this is our matrix A, and this is our vector B. And so if you work all this out and you do the least squares, what you end up with, so the least squares process gives you, after some work, it gives you the following, that your vector h, k, j of the unknowns to be solved for is equal to, and I'm going to write this out to 5 decimals because these are all decimals. You need a calculator or a computer to do this. I did it on a computer. But this turns out to be 0.87077, rounded to 5 decimal places. It didn't tell us what to round to, so I determined on my own that 5 was good enough. Again, in practice, you'll have probably some significant digits or some reason to choose an accuracy level. The second entry is 0.58809, and then the last one is 7.63118. And so again, this is to 5 decimal places, rounded. All right, and so what this means then is that we've got our h, right? We've got our h, we've got our k, and then we've got j. Remember, j, though, is not exactly part of our solution. J is going to be this, right? So my color coding is messed up. But j is going to help us solve for rho, or rho squared, because our solution is going to be this, right? The equation of the circle. So we just have to put this all back together now, and so then we remember that rho squared must be equal to j plus h squared plus k squared. And so again, I worked that out. I used the computer to help me, but I got that this is then going to be 8.73527. So I did this computation first before rounding, and then I rounded it, as you always should, right? But there's our rho squared. And so now we just put all of this into the equation to get our best fit circle. So we now have our equation for the circle. So the circle is x minus h, so x minus 0.87077 quantity squared, plus y minus k, so y minus 0.58809 quantity squared, equals rho squared, and that's exactly this number, right? 8.73527. And so there's the best fit circle for this data that we were given here in this table, just these 4 points. You can imagine just this one was messy enough, and we had to use a computer to solve it with just 4 points, and you need at least 4 points to do this, or at least, I guess, at least 3 points. There's 3 unknowns, right? But usually you'd have at least 4 points or more to solve this by least squares. You can imagine, though, if you had 100 points, which would give you a better information about what the best fit circle should be, then it would take a lot more work, right? You would definitely absolutely need a computer at that point. So in your mind, those of you, especially those of you who are interested in programming and computer code, try to think of how you would write out an algorithm to compute all this for you. Have a computer compute all this for you to give you back your least squares solutions for the best fit circle, a given data set. All right, but I'm going to leave this here for this lecture, and I'll talk to you guys in the next one.